Hi. Okay. Thank everyone. And so I'm Wuming Gong from Lehigh Heart Institute of University of Minnesota. So in this talk, I'm presenting our tool, Proformer, a hybrid Macaron transformer model that predicts expression value from DNA sequences. So our method won the third place in primary report. So the breakthrough with measurement of these electrical activity units random promoters provide us the opportunity to systematically decode the cis-regulatory logic that determine the expression values. So in this game challenge, we developed an end-to-end transformer encoder transformer to predict expression value from DNA sequences. So the Proformer used a Macaron transformer encoder architecture where two half-step feed-forward layers at the beginning and end of each encoder block, and a separate one-dimensional information layer was inserted at the first feed-forward layer in front of the multi-head attention layer. So we tested two architectures at the top of the transformer. One is the global average pooling, the other is multiple expression building. So the global average pooling layer at the top of the neural network is very commonly used for the regression and the classification tests. However, we found that when applying the global average pooling layer at the top of a very large transformer model, the whole model sometimes fails to converge on training on relatively small amount of data. So in order to address this issue, we propose a new design where where the model multiple values through multiple paths, and we take the average of prediction of the final one. So at the same time, the model also can to predict randomly masked DNA nucleotides. So in order to systematically design the right global average and the various multiple expression patterns mass building, we trained the model on 10% of the data provided by the organizers and evaluated on 2% of the data. For multiple expression paths, we also examined their performance over different number of paths, ranging from 1 to 64. Overall, we found that expression paths with mass building is better performance than average global average performance. Was achieved at the dimension size of 128 and the Macaron size, block size of 8. We also see that the models actually become larger and deeper. The global average pooling become very difficult to converge. So in comparison, the multiple expression heads with mask fielding actually produce very stable results, even when the model getting very large. So to test if our observation design can actually generate like different scenarios, design another path. We build models trying to predict ATAC-seq signal from DNA sequences. So the ATAC-seq is a technique to measure the content accessibility across the whole genome. So we sampled 100,000 genomic surrounding ATAC-seq summit, and we trained different models on 80% of data and test on the remaining 20%. So the global, you can see that global average pooling performing very well when the model is relatively small compared with the data. But when the model gets very large, we observe similar trend that global average pooling tend to fail on very large over-parameterized model. So the best performance was actually achieved by using the expression head design with dimension size of 128 and the block size of 4. So we use global average pooling for our design for the final Proformer model. So the whole model consists of two laws. One is the law, which the model trying to do the regression task, The other is mass computing test model trying to impute the randomly masked nucleotides. So we trained the model for the final summation by using a dimension size of 512 and the block size of 4 on 90% of the data provided by the organizers and evaluated on the remaining 5%. So we used a point after the epoch when the validation Pearson's R was maximized. So the similar to what we saw in 10% of data, multiple extraction heads with mass computing a better performance than the global average pooling on the validation data. So we used camera in the final model. We used camera size of 10 and with 32 expression heads. So the final model has around 47 million trainable parameters, way larger than the number of samples. The model was implemented by TensorFlow 2 and trained on 4 A100 GPUs. So we vary the learning rate over the course of training according to the formula used in the original transformer paper. And we use the warm-up step of 500 and the batch size of 512. So the ablation study actually shows that when using only one expression head, the final model performance is very similar to global average pooling. However, when we use the 32 expression head mass computing, we see a significant improvement over the holdout validation data and produce the highest weighted scores. So it's interesting that adding a GLU activation to the expression head produces even higher unweighted and experiment row on the holdout validation data. However, the weighted score is getting worse. So it's in the future, it's worth to explore different design of expression heads. So with that, I'd like to thank the challenge organizer, all participants, the China University ET Lab, and all the supports from Lehigh Heart Institute. So we thank the Minnesota Supercomputing Institute for providing the computing resource. And we thank Deep Genomics for providing the travel grant. Thank you. I'd like to take questions.
Thanks, Wuming. Any questions for Wuming on the challenge?
So I think global average pooling was breaking for your model architecture when you were going deeper, right? So do you think maybe it could have worked because if you just reduce the dimension with some fully connect pooling, then using some layers, then again pooling instead of doing a whole pool of a lot of features?
Yeah, so yes, good question. So we actually, so first of all, there's a trend in the domain that as long as you can train very large model, you can always get better performance. So our focus at NVIDIA is trying to train very large model. So before the model, the starting class, we always see that basically the more fragments you put there, the better the performance. However, as a point, when you increase the number of fragments, especially the blocks or dimensions, the model just starts to become very unstable. Even we actually reduce, for example, learning rate and some other fragment tuning. So I think we just need some organization trying to make the training more stable. So I think that this new design is just hyper-organization.
Yeah.
Trying to make the training of the large model.
Yeah. And so when you use that additional loss of I think that it's a variant of reconstruction loss. So in the architecture, was it still the global average pooling?
We use actually the multiple different paths.
Oh, okay. Sorry. I think I got it. Okay.
Yes.
Yeah.
We use one, I think, which is similar to global. Somehow we found that we can use multiple, and actually that's helpful.
Okay. Thank you.
Like